Hello and welcome to Group Workshop 1, Video Lesson 2. In this video, we will discuss the sodium-potassium ATPase, aka the sodium-potassium pump. The sodium-potassium pump is a carrier protein. Specifically, it is a co-transporter, meaning that it moves multiple molecule types at the same time, sodium and potassium. It is also an antiporter. This means that it moves those two molecules in opposite directions, one into the cell and one out of the cell. You can see in the image at the right that it moves sodium, the orange spheres, out of the cell, while moving potassium, the blue spheres, into the cell. And as we learned in the previous video, it is an active transporter, meaning that it needs ATP to move these molecules. The reason it needs ATP is because it moves both sodium and potassium up their respective concentration gradients. Specifically, for every ATP used, it moves 3 sodium atoms out of the cell, where sodium concentrations are already high, and moves 2 potassium atoms into the cell, where potassium levels are already high. Here are the steps to how the sodium-potassium pump operates. Now, I should mention that this is currently a decently supported theory, but cell biologists are still not 100% certain this is how it works. Anyway, the first thing that happens is sodium loading into the pump. Then ATP arrives and cleaves off a phosphate, which binds to the pump. The binding of the phosphate causes the pump to change conformation and release the sodium. Potassium from the outside of the cell then loads into the pump, causing the bound phosphate to be released. This causes the pump to return to its original conformation, releasing potassium into the cell. Let's look at each of these steps a bit more closely. The first step is sodium loading into the cell. We can see our purple sodium-potassium pump here. Above it is the blue extracellular fluid, and below it is the yellow cytoplasm. Notice that the sodium is coming from the cytoplasm and is binding to the inside of the pump. Now that sodium has bound, ATP shows up. To get energy from ATP, we have to break the bond of one of its 3 phosphate groups, which is being shown here. One phosphate, represented by the capital P, is cut off from ATP and binds to the sodium-potassium pump. Since ATP has lost a phosphate, it becomes ADP. The binding of that phosphate group causes the pump to change shape. Notice the open side of the pump now faces the extracellular fluid. Also notice those slots that the sodium was bound to before are now all squished. Our 3 round sodium atoms can't stay bound to that, so they are released into the extracellular fluid, which had a high concentration of sodium already. However, on the right side of the pump there are some slots that are the perfect size for our square potassium molecules to come and bind, and so 2 extracellular potassium molecules bind to the pump. The binding of those potassium atoms causes the phosphate group to unbind from the pump and go back into the cytoplasm. Because the potassium group unbound, the pump returns to its original shape. Now the open side faces the cytoplasm once again. Notice also that the slots holding the 2 square potassium atoms are now all squished. Thus, the potassium can no longer stay bound, and so they are released into the cytoplasm, which already had a high potassium concentration to begin with. And now the process can start back over. 3 cytoplasmic sodium atoms can bind, ATP cleaves off a phosphate, which binds to the pump changes conformation to release the sodium out of the cell. 2 extracellular potassium atoms bind, causing the phosphate group to release, leading to a change back to the pump's original conformation, leading to the release of 2 potassium atoms into the cytoplasm. And then it starts again, as long as we have ATP anyway. So why do we bother pumping out sodium and pumping in potassium? Several reasons, actually. First, the sodium-potassium pump helps to compensate for the leaky plasma membrane. There are a number of ion channels all along the plasma membrane that allow certain ions to flow freely down their concentration gradients. That includes channels for sodium and potassium, which means that sodium is constantly flowing into the cell and potassium is constantly flowing out of it. If we want to maintain high cytoplasmic potassium and low cytoplasmic sodium, we need that pump to do some work. The large sodium gradient produced by the sodium-potassium ATPase helps power secondary active transport. The example we discussed in the previous video was the sodium-glucose transport protein, shown here again. It is able to move glucose up its concentration gradient into the cell because it also moves sodium into the cell down its concentration gradient. The reason we have all that sodium to move into the cell is because the sodium-potassium pump pumped it out in the first place. The sodium-potassium pump also helps regulate cell volume. Keep in mind that it always moves 3 molecules out of the cell and 2 molecules into the cell. Water always moves via osmosis to where there are more solutes. So every time the sodium-potassium pump acts, it moves more solutes out of the cell, which means water will also leave the cell. This becomes especially important if the cell starts to swell with water. We can increase the activity of our sodium-potassium pumps to move more solutes out of the cell, and then water will follow via osmosis. It also helps maintain the negative charge of the cell membrane. Membrane potential means the potential or charge across the plasma membrane. The cytoplasm of a cell is always a bit negative compared to the extracellular fluid, which is important for many physiologic processes. Since the pump always moves out 3 cations, aka positive ions, and moves in only 2 cations to replace them, every time it pumps, it causes the cell's net charge to decrease by 1, keeping things nice and negative. The sodium-potassium pump uses ATP for energy. All energy is harnessed heat. And in fact, the cleaving of a phosphate group from ATP causes a lot of energy to be lost as heat. That heat is useful though, as it helps us to maintain our internal body temperature. If we are ever too cold, we can even increase the activity of the sodium-potassium pump and get warmer. And that is going to wrap up this lesson video. You should now be ready to take the quiz on ELC. Please complete that quiz before 11:59 p.m. the night before our group workshop to earn your points for it. Remember, you can take it as many times as you need to. See you in class. Probably looked really bored the whole time I was making this, didn't I? Because I'm like looking down over here. Sorry about that, but I promise you I wasn't bored doing this. You might have been bored watching it though. I don't know. This part's also not captioned, by the way. The captions are over, but I think that's okay. Anyway, bye-bye.